Imagine a future in which the vast oil sands of Alberta are no longer synonymous with combusted hydrocarbons but with the lightweight carbon skeletons of wind turbine blades, hydrogen tanks, and next-generation aircraft. That future may arrive sooner than many believe, because the same viscous bitumen now refined into gasoline can also be transformed into a high-performance carbon fiber whose production cost and carbon footprint undercut today's acrylonitrile-based benchmark. In the next 10 minutes we will trace the scientific logic, the industrial reality, and the environmental arithmetic behind this pivot from fuel to fiber. Begin beneath the boreal forest, where bitumen, thick, aromatic, and heavy, accounts for more than 170 billion barrels of proven reserves. Only about 15% of that material, the asphaltene fraction, interests us today. Rich in condensed polyaromatic rings and deficient in hydrogen, asphaltene is, in chemical terms, halfway to graphite. When it is separated from lighter molecules and gently cracked, it self-organizes into a liquid crystalline pitch. That mesophase pitch can be drawn into thin, glossy filaments, oxidatively stabilized so they will not melt, and then heated under inert gas until every lingering heteroatom departs in clouds of water, carbon monoxide, and sulfur dioxide. What remains is a turbostratic ribbon of carbon whose tensile strength rivals steel and whose modulus can exceed 400 gigapascals after graphitization. Why does this matter? Because conventional carbon fiber is born from polyacrylonitrile, a polymer whose monomer is derived from, yes, propene and ammonia, but only after an energy-intensive M-oxidation step. Acrylonitrile prices hover around $2 per kilogram. Asphaltene pitch, by contrast, costs mere cents. Melt spinning eliminates the toxic solvent bath that pan requires, and thermal yields climb above 60%, granting an inherent process energy advantage. Recent techno-economic models place the all-in cost of bitumen-derived fiber below $11 per kilogram at a 5 kiloton plant, almost 30% cheaper than its pan counterpart. Economics alone will not sway a carbon-conscious world, so let us consider emissions. Life cycle inventories compiled for Alberta's Carbon Fiber Grand Challenge indicate 6 to 8 kilograms of CO2 equivalent per kilogram of fiber when kilns are electrified, a 70% reduction relative to pan. More importantly, diverting bitumen from combustion avoids the downstream release of roughly 400 kilograms of CO2 that gasoline would emit per barrel. The fiber itself sequesters carbon for decades inside composite structures, transforming an emissions source into a material sink. Scale is often the skeptic's final refuge. Would global fiber demand, about 150 kilotons last year, ever accommodate oil sands volumes? The answer is reassuring. Dedicating a single percentage point of Alberta's annual bitumen production to fiber could supply 1/6 of projected 2030 demand without flooding the market. Pilot plants funded through the Grand Challenge are already running continuous tow lines, and a 20-ton per year open access facility is scheduled to commission early next year. Academic groups have demonstrated spinning speeds an order of magnitude faster than early prototypes, while plasma and photothermal oxidation promise to compress the slowest step in the entire process, the hours-long oxidative bake, into minutes. Nevertheless, challenges persist. Feedstock heterogeneity means that every ton of asphaltene carries a slightly different cocktail of metals and sulfur, each capable of sabotaging fiber uniformity if not removed or passivated. Rheology control at industrial scale requires exquisite temperature gradients. A Mistoon spinneret can freeze the mesophase or let it drool uncontrollably. Capital intensity, roughly $75,000 per annual ton of capacity, still dwarfs that of conventional melt spinning plants. And downstream, composite manufacturers accustomed to pan surface chemistry must validate sizing agents that marry pitch-based fibers to epoxy or thermoplastic matrices without compromising interface strength. Yet these are engineering problems, not scientific showstoppers. History suggests that when cost and performance align with a climate dividend, adoption accelerates. Aluminium needed a breakthrough Hall-Héroult cell, silicon photovoltaics required crystal growth on meter scales, lithium-ion batteries awaited cobalt-free cathodes. Bitumen to carbon fiber stands at an analogous threshold, armed with pilot data, policy incentives, and a strategic imperative to monetize resources in a decarbonizing world. When you next see a carbon fiber bicycle frame, a compressed gas cylinder, or the spar of a turbine blade, remember that its elegant black weave may one day originate from the very reservoirs once blamed for climate inertia. Turning heavy oil into high-value fiber is not merely chemistry, it is a narrative of industrial renewal, where the liabilities of yesterday become the assets of tomorrow. If this transformation intrigues you, explore the links in the description for deeper technical reports and our extended interview with the engineers behind Alberta's pilot line. Subscribe for more deep dives into materials that matter, and share your thoughts below. The journey from bitumen to fiber has only begun, and its trajectory may well redefine the carbon economy.